Well, I haven't made a video about the sun in quite some time, and I can tell anyway, because how hard it was to get to the footage, first of all, from the different websites, and how hard it is to even create this video, how hard it is to even talk about the topic. But anyway, these are images of the sun from the last year. We can see that we're starting to see some activity on the sun. Um, and in the last few weeks, there's been some sunspots on the solar face. This image is from May of last year, which shows a very active sun. What's interesting is the difference between the end of this solar cycle and the last one. At the end of the last solar cycle, we went 787 days with a spotless sun. Um, and this time they're talking about there being 40 days without a spot on the sun. So it's quite interesting. Quite an interesting start to a new solar season. And what made me look at the sun in the last couple of weeks was mainly that I started to see storms on Friday. We saw the rain that hit Australia. We saw the storms that hit Iceland. And I was looking at Google Earth, looking at the weather, and I was like, where are all these storms? Where's all this energy coming from for these storms? And they come from the poles and they send the energy out from the North and South Pole. So I started looking at the sun, and sure enough, we have the first sunspots on the sun for the next cycle. So there's a lot of this creates a lot of contention in terms of what people understand for the energy of the sun, how immediate it is, and also where the planets are. So I'm making some predictions on this. I'll put them in the text, and here's some mix of some footage from the 70s to do with magnetic fields. I just thought I'd share it. Hope you enjoy. Thanks for your time.
This is a computer simulation showing how the Earth and a global aurora would look from on board an orbiting satellite. A special camera on such a satellite could send continuous pictures of the auroras back to Earth.
And sure enough, we saw the plasma coming directly in.
By the late 60s, solar wind plasma had been found penetrating the front of the magnetosphere to the polar zones. Within the magnetosphere, dynamic plasmas, immensely greater than the Van Allen belts, were mapped around the Earth and into the tail, and particles from the tail were found moving back thousands of miles to Earth, perhaps in some way to ignite the great auroras. But great movements require great energy, so there was still the mystery of where such energy to create the great magnetosphere movements, of which these auroras were but a tiny visible fraction, came from. The magnetized solar wind rushing at the outside of the magnetosphere, it was suggested, could transfer energy to drive the movements within the system. But if so, how? A dynamo-like action would be transferring energy from the wind into the magnetosphere, sufficient energy to power what was emerging as a fundamental process within the system which might for the first time really explain the auroras. For the great auroras were now perceived as the possible end product of a fundamental and mysterious process within the magnetosphere, a vast process which was now being named the substorm. But what exactly this key substorm process in the magnetosphere was difficult to dig out. This became the next mystery to overcome.
Buried in there is the mechanism for generating the auroral lights. We know that the solar plasma is flowing from the sun. We know it impinges and interacts with the Earth's magnetic field, which we can measure, of course, at the surface of the Earth. It interacts in such a way is that these particles get accelerated into the atmosphere, much like, in your own TV set. The screen is the atmosphere, and the nature's program is not soap opera or something. It's the actual aurora dancing across the sky. And the real mystery now to us is not that the plasma comes from the sun. We know that now, the actual particles, and that they impinge upon the the atmosphere to form light. What's the problem is that there's a high voltage power supply hidden within this magnetosphere, the actual mechanics for generating the beam that causes the light.
In 1895, Birkeland was very much occupied with the new discoveries of cathode rays. The thing was that he had got the idea that cathode rays, that is electrons, were sent out from the sunspots. And he knew that the aurora had similar periods as the sunspots period. And his idea was then, which was a new one, that the aurora was produced by cathode rays emanated from the sunspots. And his idea was now to study cathode rays under the influence of magnetic fields. And then he determined to construct a model of the globe and expose it to cathode rays and study how the rays moved. He found that the cathode rays penetrated, they hit the Earth on the night side, as you should expect, if they were origin of the polar light of the aurora. Birkeland mentioned some of his results to Professor Störmer, and he thought it might be an interesting mathematical problem to calculate the trajectories of electrons in the magnetic field of a terrella, of a dipole. And he started then on just this famous study of northern light.
At first, researchers could see only the bland white face that is revealed by visible light, and sometimes the procession of mysterious dark spots that some took to be clouds. The Earth's atmosphere clouded and distorted the image. But in time, the great solar telescopes like Big Bear in California blew away the notion of a placid, unchanging sun. People wondered what the sun was made of, but never expected to know it's 93 million miles away. The answer was discovered in the colors of the sunlight itself. As each element burns, it consumes its own distinctive color, writes its own signature in a dark line across the spectrum. Our sun is mostly made of hydrogen and helium, some carbon and iron and other elements, much the same elements we're made of. But that's not surprising, since we are born of the same stars.
Before you die, let me show you the things I have done, so you understand the breadth of my transformation. This is me at the Grand Canyon. Do you see? This is me at Mount Rushmore. Do you see? Do you see?
Yes, I see.
Here I am at the Alamo in San Antonio. This was just outside the gift shop. Do you see? One thing that we never use. Sir, you know, what's that one thing that starts with an R that we never use? Restraint? Yeah, restraint. Well, check this guy out, but let's use some restraint. Look at the things I've done. Here I am at Yellowstone National Park. Do you see? Here are pictures of my trip to Cheyenne for Frontier Days. Do you see?
Oh, God.